Hello everyone and welcome to this video. The goal of this video is to present a brief introduction to the LAMMPS software. So in the last video we talked about the basics of molecular dynamics simulation, and although the algorithm for molecular dynamics is not that difficult, so we talked about the 4 steps that are needed to perform a molecular dynamics simulation, which is to calculate the energy between the atoms, based on that calculate the force, and then based on that calculate the acceleration, then perform a numerical integration to calculate the change of the position. So all of those things are not that complicated to program or to code yourself, but in practice, in our group, we always use the LAMMPS software to perform those molecular dynamics simulation, because this is a very well-established software. It can do a lot of interesting features and it makes life easier. So here I'm going to give you a few basic information about the LAMMPS software, about the convention that I used in this software, about the types of information that you need to provide LAMMPS in order to perform a simulation, and the types of information that LAMMPS will give you in return. And we will see this by looking at an example for a simulation which consists in generating a silica glass. So LAMMPS is actually an acronym it stands for Large Scale Atomic Molecular Massively Parallel Simulator. And it's, as I mentioned before, a very well-established software to perform molecular dynamics simulation. It might be one of the most used software for this kind of simulation. So the good thing is that there's a lot of users for this software, so it's easy to find some help online on how to use this software, or if you're facing an error message or anything like that. It can do other things than just purely molecular dynamics simulation. It can be used for energy minimization or Monte Carlo or grand canonical Monte Carlo, also peridynamics simulation. But here we will mostly review how to use it for molecular dynamics simulation. So it's pretty versatile software in the sense that it can simulate like very small system, like a few atoms, just a few molecules, up to potentially billions of particles. But of course, the more atoms you have, the slower the simulation will be. So it's a free software. It's also open source, so you can have a look at how it has been coded and modify it, add the functionality that you want. And it's presently available in C++. And it's maintained and offered by the Sandia National Laboratory, who initially coded this software. So you can certainly run LAMMPS on your laptop if you wish. You can install it on Mac, on Linux, Windows, or whatever you want. But it's more optimized for a large supercomputer, for clusters. And as soon as you will want to run a simulation that contains more than a few hundreds of atoms or for extended periods of time, it's going to be very important that you run it on a cluster. Otherwise, your laptop will certainly not have enough power or it's going to take a very long time for the simulation to finish. So if you are in my group at UCLA, we have already the LAMMPS software installed on Hoffman. You can access it using the lamps.q command. We also have some new version of this software, newer version of LAMMPS that we just compiled ourselves, and that will be available on the Google Drive directory. So we will be using LAMMPS to perform molecular dynamics simulation. But of course, to do so, we will need to tell LAMMPS what we want the software to do. We will tell him what are the instructions that we want it to do. But to do so, we have to make sure we speak the same language as LAMMPS can understand. So we have to be aware of what are the conventions that LAMMPS is using, what are the units, how to properly define all the parameters that needs to be provided to LAMMPS. So the first thing is to define the geometry of the system that you will be simulating. And this can be accomplished by defining the size and geometry of the simulation box. So the simulation box is the box where the atoms will be contained. Okay, so this is going to be the extent of the space where the atoms are able to move. LAMMPS can simulate different types of simulation box, can be cubic, can be monoclinic, can be triclinic, etc. So different types of geometry and different sizes. But in the following, we will mostly focus on cubic boxes. The reason is being it's the most simple. So in a lot of cases, it's just fine to use a cubic box with all the angles between 90 degrees and the size of the box being the same on the X, Y, and Z direction. And to define this cubic box, what LAMMPS will need is for each axis, on axis X, axis Y, axis Z, LAMMPS will need you to provide the location at which the box is starting and the location at which the box is ending. For example, if you look at here on the axis X, what you will need to provide is the position X low, which is the lower bound on the X-axis of the box, and the position X high, which is the higher bound of the cubic box on the X-axis. So you will need to do the same for the X-axis and the Y-axis and the Z-axis. So for example, on the Y-axis again, you will need to define Y low, which is the lower bound on the Y-axis, and Y high, which is the higher bound on the Y-axis, etc. And usually what we will use in practice is that we will always define one corner of the box to be at 0, 0, 0, so the origin of the coordinate system. So we will usually define X low, Y low, and Z low to be 0, so that X high, Y high, and Z high are just located at the same distance from the origin, which is going to be the size of the cubic box, okay, the size of one edge of the cubic box, corner of the box. Then you will need to define the coordinates of all the atoms within the cubic box, okay, and this can be accomplished by just providing to LAMMPS the Cartesian coordinates of each of the atoms. So for each atom P, what you will need to provide is its position with respect to the origin, and if you take the origin at 0, 0, 0, the position will be just the X, Y, and Z coordinate of each atom within this box. The next step will be to define what happens at the boundary of the simulation box. So the first option is to define, for example, a non-periodic boundary, which means that if you have an atom and if it moves and it goes toward the boundary, either the atom will bounce back or the atoms will just be lost, or the simulation box will be increased in order to contain the new position of the atom. So you have different options in LAMMPS. Those are for non-periodic boundary condition. The second option, which is usually the one we will use, is to use periodic boundary condition. So why would we want to do that? Because if you are using a non-periodic boundary condition, what it means is that you are simulating a surface. And since you are simulating here a very small system, then the surface is very large as compared to the size of the system, which is typically not realistic. In real life, atoms are very large, and the surface is a very low fraction of the system itself. But here, the surface is a very large fraction. It's very large as compared to the size of the system. So typically, we don't want to simulate a small system that is surrounded by a surface. What we want to simulate is an infinite bulk system. Okay, we don't want to have the spurious effect that is induced by the presence of a surface. And one way to avoid that is to use periodic boundary condition. The idea behind this is that you will define a simulation box, and what you will say is that this simulation box is actually replicated periodically on the X, Y, and Z axis. Okay, so the idea is that all the atoms that you have inside this simulation box, actually you will have the same fictitious atoms being replicated in all the three directions. So why do we do that? Because now if you have an atom that moves here and goes out of the simulation box, it means that it will now be here, it will be displaced in a fictitious box on the right. But since all the boxes are the same box that are replicated in the free direction, it means that this atom will now also be here. So in practice, if you use periodic boundary condition, it means that if you have one atom that moves and go out of the box, it effectively come back from the other side. So that's why it's called periodic boundary condition. You have one atom moving on the right, it comes back from the left. We have one atom going on the top, exiting from the simulation box, it will come back from the bottom. So that's one way to ensure that first you don't have any surface, there is no surface in the system, and the atoms can never leave the box. The atoms are always going to be contained in the box. If they live on one side, they come back from the other side. The way to express this mathematically is that if you have a simulation box like this with a size Lx on the x-axis, so you have an axis x that goes from 0 to Lx, okay, this is the axis x, and you have one atom here that moves and end up at a position x, which now becomes larger than the size of the box. Then the atoms will go back on the right. Okay, this distance here will be the same as this distance here. So its new position x prime will be calculated as follows. The new position x prime will be the position that it would have x if it was free to leave the box, but because it is not leaving the box, because it is coming back on the left, then you are removing the size of the box Lx, okay, and this gives you the new position x prime, the position x that it would have minus the size of the box tells you the new position x prime that the atoms will have due to the periodic boundary condition. So you have to be a little bit careful about periodic boundary condition and what it means, because if you have, for example, two atoms, 1 and 2 like this, one is at a position x1, one is at a position x2. So those two atoms are very close from the boundary x and Lx. So the question is, what is the distance between those two atoms? So you would think that maybe the distance, if you just look at it like this, would be the absolute value of x2 minus x1. This would be the real distance between the atoms if there was no periodic boundary condition. But because of the periodic boundary condition, atom 1 is also located here. There is a replication here of atom 1 due to the periodic boundary condition. So the real distance between atom 1 and atom 2 should be this distance here. So the real distance between atom 1 and atom 2 can be calculated as, again, the size of the box, so Lx, minus the distance that they would have if there was no periodic boundary condition. So you always have to be careful when you have two atoms, you want to calculate their distance. Always wonder is, if I take the distance between the two atoms, is their real distance the real distance that they would have even in the absence of periodic boundary condition, or is there one of the replicates of the atoms that is actually closer than the real atoms themselves? And you should always take the smallest possible distance. The smallest distance is always the real distance between each pair of atoms, because the shorter the atoms are, the closer they are from each other, then the higher will be their interaction energy. So this is the distance that should be taken into account. The next step is to define what kind of dynamics do you want LAMMPS to simulate. For example, do you want the volume to be fixed? And if the volume is fixed, the pressure can vary, and LAMMPS can calculate what pressure will you have for a given volume. Or do you want to fix the pressure? But if you fix the pressure, then the volume of the system can vary. If the pressure becomes too large, the system will shrink. If the pressure becomes too low, then the system will expand. So you always have to wonder what are the thermodynamical quantities that are fixed, the volume, the temperature, the pressure, etc. What are the ones that are free to change? Okay, so this defines the thermodynamical ensemble in which you would like the simulation to be performed. So you always have to define, for example, do you want to fix the number of atoms? Do you want to fix the volume? Do you want to fix the energy or something else? For example, you always have to choose whether you want to fix the volume or you want to fix the pressure. You cannot fix the volume and the pressure at the same time. If you fix the pressure, then the volume will change in order to reach the pressure that you want to fix. But if you reach the pressure, then the volume is going to change. If you fix the volume, then the pressure is going to be determined by the volume that you are fixing. You cannot at the same time decide what the volume should be and what the pressure should be. You have to define one or the other. And it's the case also for the energy. You can choose to fix either the energy or the temperature, but you cannot fix both at the same time. And you have to choose whether you want to fix the number of atoms or the chemical potential. So all those properties are coupled to each other, and for example, the number of atoms, volume, and energy are extensive properties, whereas the chemical potential, the pressure, and the temperature are intensive properties. And for each extensive properties, you have a corresponding intensive properties. So an extensive property is, for example, if you take the volume, you take the whole volume of your system, you can divide it in two parts. You can always say that the volume of your system will be the volume of the subsystem 1 plus the volume of the subsystem 2. This is for an extensive property. If you have an intensive property, like the pressure, then if your system is at equilibrium, the pressure of the total system will be equal to the pressure of the system 1 plus the pressure of the system 2. So you can write that the total pressure will be pressure of 2 and will also be pressure of 1. This is for an intensive property. If they are at equilibrium, then the pressure of each part of the system should be equal to each other. Same for the temperature. The temperature of the whole system should be equal to the temperature of 1, which should be equal to the temperature of 2. So for each extensive property like the volume, you need to choose whether you want to fix this extensive property or the corresponding intensive property. Same thing, you will need to decide whether you want to fix the total energy or the corresponding intensive property, which is the temperature. Usually, we will always want to keep constant the total number of atoms, but there are some cases where the number of atoms is not constant, and in that case, what will be fixed is the chemical potential, which is the corresponding the intensive property that corresponds to the extensive property, which is the number of atoms. So whenever you want to perform a molecular dynamics simulation, you need to define what are the thermodynamical quantities that are going to be fixed. For example, if you fix the number of atoms, the volume of the simulation, and the total energy, this is the microcanonical ensemble. This is called the NVE ensemble. If you want to fix the number of atoms, the volume, and the temperature, okay, so if your system is in contact with a given atmosphere, a given thermostat, then it's not the energy that is fixed, it's the temperature. The system has to have the temperature of the thermostat. In that case, this is called the canonical ensemble, and this is called NVT. Those are the quantities that are fixed. It means that in this case, for example, the energy might be changing during the course of the simulation. And finally, if what you want is to simulate a system that is at a constant temperature, for example, 300 Kelvin, a constant pressure, for example, 1 atmosphere, the pressure that you experience in normal atmospheric pressure, then you are working in the isobaric ensemble, which is called the NPT ensemble. The next things that you need to pay attention to are the units. The reason for this is that you will need to provide a lot of parameters to LAMMPS. Those are the parameters that will dictate what type of simulation you want to perform. For example, if you want to perform a simulation at a given temperature or a given pressure, then you will need to provide to LAMMPS what is the targeted temperature that you want, what is the targeted pressure that you want. And for this, LAMMPS needs to know what is the units of the number that you are providing. For example, it needs to know if you provide a temperature, is it going to be in Kelvin, is it going to be in Celsius, etc. For this, you don't have to provide the units with any single number that you will provide to LAMMPS. You just have to choose which system of units are you going to work with. So this is always one of the first things that you will need to define in a new simulation. What is the system of units that you will decide to use? For example, LAMMPS will come with different possible choices, real units, metallic units, or SI units. And for each of those three systems, LAMMPS will expect that all properties will come with a given preset units. For example, in the real unit system, all mass should be expressed in gram per mole, all distance should be expressed in angstrom, all time should be expressed in femtoseconds. For the metallic system of units, for example, the energy will be expressed in electron volts and the time will be expressed in picoseconds, not in femtoseconds. So there is no right or wrong system of units. Different types of system depending on their size, depending on the typical energy, depending on the typical time that characterizes those systems. Some unit system might be more appropriate than some others. In general, we will try to always use the real system of units so that all the simulation that you are doing are consistent with each other, with the same units, etc. Next, we are going to discuss the kind of file that you will need to provide LAMMPS to be able to perform the simulation. So the way it works is that to perform the simulation, you will need to provide a given number of information to LAMMPS, which will be first, what is the initial position of the atoms, how many atoms, what types of atoms, etc. And you will need to provide some instruction, like what kind of molecular dynamics simulation would you like to run, NVT, NPT, etc., which temperature, etc. So you will need to provide some instruction. So all those initial parameters, initial instruction, etc., will be provided in the form of some input files. So a collection of files that will contain all the information that LAMMPS needs to know in order to perform the simulation. And then in return, LAMMPS will provide you back some output file, which will be the file that contains the results from the simulation. So let's start with by reviewing the different types of input files that you need to provide to LAMMPS. The first thing that you should always be very careful of is that each new simulation should be run in a new directory, which means that every time you do a new simulation, even if it's a slight variation of the previous one, or even if it's a simulation that is continuing after a previous one, you should always try to run it in a new directory. The reason is that for each new simulation, LAMMPS will generate some new output file. And if you run two simulations in the new directory, it's very possible that some of the output file will just overwrite the previous output file that were generated using the previous simulation. So in order to avoid those difficulties and the risk of losing some files, you should always try to run for each new simulation, define a new directory. And in this directory, you will provide all the input files that you need. So the initial configuration of the atoms, the system, information about the potential that you want to use, etc., all the parameters. And in the same directory, all the output file, the result of the simulation, will be provided by LAMMPS. And if you use a new directory for each new simulation, then there is no way of mixing up different simulation or having files that overwrite each other. So here is a list of the typical input file that you will need to provide to LAMMPS. The first thing is that you will always need to provide a data file. The data file will contain first the geometry of the system, the size of the simulation box, the number of atoms that you want to simulate, the types of each atom, so the number of elements. For example, if you want to simulate a silica glass, SiO2 glass, then you will need to provide that there is two types. First types will be silicons, second types will be oxygen. So you need to provide a number of different elements. And you will need to provide the mass, the molar mass of each types of atoms, each elements. And next, you will need to provide what is the initial position of all the atoms, and also potentially their velocity, although this is not required. What is absolutely required is that you put some initial positions. As you may remember from the previous video, if you do the molecular dynamics cycle, you need to start by an initial position. LAMMPS cannot guess what is the initial position of the atoms that you want, so you will need to provide their initial position x, y, and z, their Cartesian coordinates. The second thing is the input file. So all those three files are input file, but what we specifically call the input file is the file that contains all the instructions. So in this file, which we typically write the in.something, as opposed to the data file that we typically write something.dat. In this input file, what we put is all the instructions. So what types of simulation do you want to do, at which temperature, at which pressure, etc. And potentially, we will put the information about the force field, the potential parameters, although this can also be placed in a separate file. And you will also, in this file, put the information about what you want LAMMPS to give you back. Do you want LAMMPS to calculate the energy as a function of time, the pressure as a function of time? What are all the information that you want LAMMPS to calculate for you based on the simulation? All those information needs to be specified in the input file. And then the last type of file, which sometimes is included in the input file, but sometimes is provided as a separate file, is a potential file, which is a file where you would find all the information about the interatomic potential that you are using. That is to say, for example, the energy as a function of the distance between the atoms, or any other types of information that characterizes the potential, the interatomic energy, the interatomic force field acting between the atoms. Let's go through the syntax of all the inputs files one by one. So the first one is the data file. So the data file contains all the information about the number of atoms, the types of atoms, the geometry of the system, and the initial position of the atoms. So it's always important that you follow the right syntax, otherwise LAMMPS cannot understand what is the information that you are providing to LAMMPS. So it's important that you make sure you use the right keywords and that you provide the information in a format that LAMMPS can understand. So here is the typical syntax of the data file. So it always contains first a first line, which is typically ignored by LAMMPS. This is just something for you to remember what this data file is about. So it's something that you can say, what type of system is this, what types of atoms, etc. So this is just the title of the system, okay, the name of the system, or whatever information that you might want to put that is relevant to you. The second line here is to provide the number of atoms. So this provides the number of atoms, which is obviously something important because everything else will depend on that. The number, depending on the number of atoms that you have, you will need to provide a different number of initial positions. So here, every time you have something here that starts with a pound sign, then this is a comment, and this is going to be ignored by LAMMPS. This is just for you to remember what those lines are about. You are free to add comments to remember what each keyword is for, and those are going to be ignored by LAMMPS. The next line is to specify the number of atom types. In this case, you have two types of atoms. Type 1 will be silicon, type 2 will be oxygen. So you need to provide to LAMMPS the information about how many elements is your simulation will contain. The next step is to provide some information about the geometry of your system. Okay, so you need to provide to LAMMPS the information about what is the size of the simulation box, and this is provided by providing to LAMMPS the information about the x low and xy parameter, and the same on the x and y and z axis. Okay, so the way it works is that you need those three lines written in the following way, with the x low and xy keyword in each case. On the first column here, you will provide the initial extent of the box on the X, Y, and Z axis, which usually will be 0. And then the second number here provide the length of the box. Okay, so the maximum, the upper limit of the box on the Y-axis, X-axis, Y-axis, and Z-axis. So in this case, it means that you are simulating a box that has that is cubic. It has the same length on the free direction, and its length on X is close to 35, which is the same length on Y and the same length on Z. Okay, so you need to provide this information so that LAMMPS can know what is the extent of the simulation box. The next step is to provide some information about the masses. So here you will need to provide for each type of atom, each type of element, what is the molar masses of each element. Okay, so here you see that you have some numbers. Okay, the size of the box, the molar masses, and here it's important that LAMMPS knows what is the units that you are using. So you will need to provide LAMMPS in the main input file. You will need to say what is the system of units that you are using. In this case, we are using real units, which means that here all distance are to be expressed in angstrom, and here the molar mass are in gram per mole. Okay, so everything, all the numbers that you provide will depend on the types of units that you are using. And then here you need to provide the initial position of the atom. So you need to provide the keyword atoms, and then start to provide for all the atoms their information, their initial position. So the way it works is that you have for each atom you will need to say first its ID, so the number of each atom. So you have 3,000 atoms here, so you have atom 1, atom 2, atom 3, etc. And for each atom you need to provide its number. Then in the second column you need to provide its type. It's the element that its atom is. So type 1 will be silicon, type 2 will be oxygen in this case. Next is you need to provide the charge. So here in this case you need to provide the partial charge of each atom. In this case, for silicon, the partial charge will be 2.4. This depends on the potential that we are using. And the partial charge for oxygen will be minus 1.2. Okay, so we always have to make sure the entire system is neutral. So here you have 2 times more oxygen than silicons. So overall, the system will be neutral. Okay, so this is for the charge. Then the next column that you need to provide to LAMMPS here will be the position X, the position Y, and the position Z. So you will need to provide the coordinates for each atom. Okay, so the next step here, the next 3 columns will be X, Y, and Z. So in this case, for these types of atoms, you will have 1, 2, 3, 4, 5, 6 columns. First column being the ID, the number of each atoms, then the elements, then the charge, then X, then Y, then Z. Usually you will never have to write this type of data file yourself. That would be pretty long to write for the 3,000 atom, what is their initial position X, Y, and Z. So typically we will be using either a different software to generate this type of data file, or you would write a simple script to generate randomly some initial position X, Y, and Z for each atom. Or we would use the result from a previous simulation as a starting data file for a new simulation. Next, you will need to provide the main input file. So the main input file will contain all the parameters, all the instruction telling LAMMPS what to do in which order. So the way this file will be read by LAMMPS is that LAMMPS will read line by line, starting from the top and the bottom, and will either save the parameters that you provide or execute the instruction one by one in an iterative fashion. Again, so the first line here is a comment, start by the pound sign, so it's going to be ignored by LAMMPS. This is just for you to remember what each line is about. You can always feel free to comment your input file as much as needed. The second thing which is very important is the unit system. So here, this is one of the first things that you need to do, is to say what types of systems of unit are you using. And here we are using the real system, which means that all distance will be expressed in angstrom, all energy will be expressed in kilocalorie per mole, etc. Okay, so this is a very important instruction to put at the beginning of each main input file. You will need to provide what is the units, and then all the numbers that you provide to the input file, to the data file, etc., their units will be defined by this choice that you make at the beginning. Are you using real units? Are you using metal units, etc.? Then you need to provide what is the dimension of your system. So typically we work with a 3-dimensional system, so this is likely to always be 3, but that being said, if you were to simulate a 2-dimensional system, then here you would put 2. The next step is some information about how LAMMPS should allocate the simulation to different processors. So in this case, we will typically always let LAMMPS assign this in the way LAMMPS thinks is the most optimal way. So we will just leave this line as it is by just a free star symbol. The next step is to define what types of boundary condition that you want to use. Okay, so the boundary condition can be periodic, can be non-periodic, etc. So you need to define for each direction x, y, and z what type of boundary condition would you like to use. Usually we will always use P, which means periodic boundary condition. So in this case, you need to provide the types of boundary condition that you want for x, for y, and for z. And depending on the types, you will provide a different letter, P being the letter that is used for a periodic boundary condition. So usually this line will always be the same. It will always be P, 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 because you will typically want to use periodic boundary condition in the 3x, y, and z direction. Then you need to provide some information about the types of atoms. So here we say that we are going to use some charges. It means that LAMMPS will expect that we will have a collection of atoms, and each atom comes with a given charge. So there might be different types of atoms that LAMMPS can deal with. For example, you can have some atoms that have no charge, so all the atoms would be neutral with a 0 charge. Or you can simulate other types of elements like grains that interact with each other, etc. So usually we will always define the type charge for the types of system that we are interested in. The next step is to tell LAMMPS what is the initial configuration. So we already put the initial configuration into the data file. So what we just need to tell LAMMPS is to read the data file by using this command read data, and here put the name of the data file. So here you would put the name of the file where you have put all the information about the system geometry and the initial position of the atoms. At this point, LAMMPS will stop reading the main input file, will load the data file, will read all the information of the data file, and will save them. And then once this is done, we'll continue reading line by line the main input file. The next thing that you need to provide is the information about the potential. Okay, so this is very important. The simulation is only as good as the potential is good. So you will need to provide some information about what types of interatomic potential are you using, what is the expression of the energy as a function of the distance, are you using any other types of potential. So in this case, we will put all the information about the potential in a different file. So we can use the command include, which means to include another file, and in this case we need to put the name of the file that is to be included, which in this case is pot.mod, which is going to be a file where all the information of the potential is going to be provided. Again, LAMMPS at this point will stop reading the main input file, will load the potential file, will read all the information about this file, and then will continue reading the main input file. The next step is to provide some information about what kind of outputs do you want LAMMPS to provide you during the simulation. What do you want LAMMPS to calculate? What do you want LAMMPS to give you back as an outcome of the simulation? The first things that LAMMPS can give you, it can give you some information about the thermodynamics of the system. Those are going to be all the information, all the properties of the whole system. It can be the temperature of the system, the potential energy, the pressure, the density, etc. Those are some information about the whole system. The second thing that LAMMPS can tell you is some information about the atoms themselves individually. For example, what is the position of each atoms according to time, what is their velocity, etc. So there are two types of information. The information that are about the whole system, those are the thermodynamical information, and the information that are atom specific, like their position, velocities, etc. Those are atom per atom quantities. So the first thing is about the thermodynamical properties. You will need to tell LAMMPS using this command thermostyle what are the information that you want. So you will need to use a list of keywords that contains all the information that you want to get about your system. In this case, first you will want to know what is the current step number. So every time you do one steps of molecular dynamics, one molecular dynamics cycle, you do a given step, and then you will repeat this step iteratively, step 1, step 2, step 3, and each step will be separated by a given time dt, which is the integration time. So you will want first to know what is the current step, so that you can know, for example, the evolution of the temperature or of the other properties as a function of the step number. In this case, the second thing that we ask LAMMPS to give us is the temperature by using the temp keyword. The temperature depends on the velocity of the atoms. If the atoms moves very fast, then the temperature will be very high. So LAMMPS will calculate based on the velocity of the atoms what is the temperature of the system and will output it. So again, this is a thermodynamical property because this is a property about the whole system. The next step that we ask in this case is the potential energy. Potential energy, we can request it by putting the PE keyword. This means to LAMMPS gives us the potential energy. Next, we want the pressure. So this is achieved by putting the press keyword. This will give us the pressure. In this case, since we are using real units, the pressure will be expressed in atmosphere. Next, we want the volume. So this will be given, LAMMPS will give us the volume in cubic angstrom of the system. Lx is the size of the system on the x-axis. So it's the length of the simulation box on the axis x. And the last thing that we request is the density. So LAMMPS will give us the density, which is in gram per cubic centimeter, the density of the system that can tell us some information about how packed the atoms are. And this is also something that we can compare with experiments to validate the simulation. Okay, so all the thermodynamical properties that you want LAMMPS to give you, and there might be some other option. You might want LAMMPS to give you the enthalpy of the system or any other properties of this kind. You have to put here all the keywords that corresponds to the property that you want LAMMPS to calculate. So those are the thermostyle properties. Then the next step is you will ask LAMMPS to provide you the specific per atomic information. In this case, this is achieved by the dump command. The dump command will generate a separated file. So in this case, the name of the file will be md.lamps trajectory, trg. This file will contain some information for each types of atoms. For example, in this file, we will have for each atom ID. So this is the number, the ID of each atom. LAMMPS will provide you each type. Okay, so is it silicon, is it oxygen, etc. And will provide you the position X, Y, and Z. And LAMMPS will do that for after every number of steps. So how often is LAMMPS going to give you this information? LAMMPS is going to give you this information, in this case, every 1,000 steps, which means that every 1,000 steps, so step 1, then step 1,000, then step 2,000, then step 3,000, etc., LAMMPS will add in this file lamps.trajectory the ID and the position of all the atoms. So this is the trajectory file. It will contain the position of the atoms according to time. This is the file that you can use later on to see the atoms moving and how they are moving according to time, to see their motion, their trajectory. Regarding the thermodynamical properties, again, you don't necessarily want to have this information every single step. So you can ask LAMMPS to how often do you want this information. This is defined by using the command thermo and then putting here how often do you want this information. This means that you will have the thermodynamical quantities every 1000 steps. Okay, so you can request this information as often as you want, but typically you will want to put this information not too often to avoid having giant files that contains all the information about your system every single step. So it's probably usually fine to ask the thermodynamical information every 100 or every 1000 steps to minimize the size of the files that are generated. Then, so this defines all the outputs. Okay, so this defines all the quantities that you want LAMMPS to calculate for you, the information that are for the whole system or the information that are per atom. Once you have defined all of this, then LAMMPS knows about the initial configuration, about the potential that you want to use, about the output information that you want LAMMPS to provide you. So LAMMPS knows everything about the parameters of your simulation. The next step will be to provide the instruction. What do you want LAMMPS to do and in which order? So in this case, the first thing that we want to do in this case is an energy minimization. We want to minimize the energy of the system. So this is achieved by putting the minimize command, and here putting a couple of parameters that I'm not going to describe and that usually are going to stay like this. The goal of this energy minimization is because you start from potentially a random configuration, so you have some random position of the atoms. So it's always good to start the new simulation by minimizing the energy of the system. So what is an energy minimization? The idea is that you start with your simulation box like this, and maybe at the beginning the atoms are placed randomly. So it means that the initial configuration will be very unlikely. It will be very unrealistic. The atoms will not be at the right distance from each other, which means that the energy of the system will be pretty high. So the first thing that you always want to do when you start a simulation, at least most of the time, is to do an energy minimization. The idea of an energy minimization is that you are going to, atoms by atoms, you are going to slightly move them in order to optimize and minimize the energy of the system. The way it works is that you take each single atom, you try to move it a little bit on the right, a little bit on the top, a little bit in the bottom, a little bit on the left, etc. And you try to look how is the energy changing if I move the atoms on the right or on the left. For example, if you take a given atom, you can try to look at what is its energy as a function of its position. And here, if you place the atom randomly, it means that initially the atoms will not be at their optimal position. Their energy will not be minimum. So what LAMMPS will try to do is to start with the initial position of the atoms, and for all the atoms we'll start to move a little bit to the right, a little bit to the left, and here we'll determine where should I move the atoms in order to minimize the energy. So then, for example, in this case, you realize that you should move the atoms to the right. This is going to minimize the energy. You are going to move it again, etc. until the point that you find a minimum of energy. What is a minimum of energy? It is when you realize that you have an atom that if you move it to the right, the energy increase, but if you move it to the left, the energy also increase. It means in that case you have found a minimum of energy, at least a local minimum of energy. So what LAMMPS will try to do is one by one will move all those atoms iteratively by looking at where, in which direction is the energy decreasing and how to minimize the energy of the whole system. So that way you can make sure that you start with an initial configuration that is not too unrealistic. So now let's come back to the main input file. So here you will continue this file by putting more instruction. So we can put as many sequential instruction as we want, and LAMMPS will just execute all those instructions one by one. So we started by doing an energy minimization. As soon as LAMMPS will be done with this energy minimization, it will start to execute the new instructions that are given in the main input file, line by line, going from top to bottom. Here, the next thing that we want to do is we want to do NVT simulation. So at this point, we want to start doing some molecular dynamics simulation. This is accomplished by using fix NVT command. This means do a molecular dynamics simulation in the NVT assemble. So this is the canonical assemble. It means that we want to fix the number of atoms. So the number of atoms will be fixed. We have already said that there should be 3,000 atoms. We want to fix the volume. So it means that at this stage, the volume of the simulation box is fixed. So the pressure will be adjusted accordingly. The pressure will be calculated accordingly, but the volume cannot change. Here, the volume is fixed, so it remains the volume that we provided in the data file. And then we need to provide the initial temperature. We need to provide the temperature that we want the molecular dynamics to be performed at. So here, what we would like to do is a steps where we want to perform a glass. So what we want to do is we look at the temperature according to time. What we want is to start at very high temperature, which is in this case 5,000 Kelvin. This is to make sure we melt the system. So we will want to melt the system at very high temperature for enough time. Then we want to quench the system by decreasing the temperature very fast to cool the system to room temperature, but cool it fast enough so that it doesn't have enough time to crystallize. So this will be the second step. This will be the cooling stage. And finally, we want to relax a little bit more the system at 300 Kelvin, which is room temperature. So we want to do all those phases iteratively. This is how, at the end, you can form a glass. You start from a liquid that is mixed and melted at very high temperature, and eventually we expect to get a glass as an outcome of this simulation. So the first step is to do this NVT simulation at very high temperature. The reason, besides melting the glass, is that we are not sure that the initial configuration that we provided is realistic or not. So we need to mix the system at very high temperature. So the atoms are going to move very fast with respect to each other. This is to make sure we lose the memory of the initial configuration. The atoms will be moving so fast that they will not remember where they come from. So after a few picoseconds of molecular dynamics, the atoms will not remember where they come from. So the initial configuration that you provided will not be relevant anymore. You will have a new equilibrium condition for a liquid at 5,000 Kelvin. So here you need to provide, in this case, you don't need to provide the pressure because the volume is fixed, so the pressure will be calculated. This is not something that you fix. And you need to provide the temperature. So here, those are the two numbers corresponds to the temperature. So this means 5,000 Kelvin. The reason you put two numbers is that you should always put the initial and the final temperature. So this means in this case that LAMMPS is going to do a molecular dynamics simulation in the NVT assemble with a temperature that is initially at 5,000 and will eventually be at 5,000. It means that in this case, the temperature remains stable at 5,000. But for example, in the cooling stage, we will want to decrease the temperature starting at 5,000 and eventually reaching 300. So in this case, the initial temperature will be different than the final temperature. But whenever the temperature is not changing, then those two numbers must be the same. The next thing is that you need to provide this number here. This is the damping factor. So we will talk more about the meaning of this factor, but you can think about this number as how often do you want LAMMPS to adjust the temperature of your system. So the way LAMMPS is working is that you fix the temperature that you want. In this case, you want the temperature of your system to be 5,000 Kelvin. How does it work? The main idea behind this is that the temperature is given by the velocity of the atoms. If the atoms are moving too fast, then the temperature might be higher than the one you want. And if the atoms are moving in a slower fashion, if the temperature is too low, then it means that the atoms are not moving fast enough. So the way it works is that you impose a temperature. Here you impose the temperature to be 5,000, and LAMMPS will try to adjust the velocity of the atoms. If the atoms are not moving fast enough, LAMMPS will accelerate the atoms. If the atoms are moving too fast, then LAMMPS will slow down the atoms. And LAMMPS will try to do that every 100 steps in this case. So if you put a high number here, if you put 1,000 instead of 100, it means that LAMMPS will adjust the velocity of the atoms less often. If you put 10 instead of 100, LAMMPS will adjust the temperature more often. So it will keep checking if the system is too hot, too high, and will adjust the velocity of the atoms accordingly. Okay, so this depends on the types of thermostat that you are using. Here in this case, we are using a Nose-Hoover thermostat. So this is in practice more complicated than what I just said, but you can typically try to understand this as follows. So typically a good order of magnitude is for this number should always be 100 times the time step. Okay, so in this case, the time step that we are using will be 1 femtosecond. So in this case, this number will be 100 femtoseconds. So this is a typical time. This is the time in between each time that the velocities will be rescaled in order for the temperature to remain around 5,000 Kelvin in this case. The next step is we want the system to be at zero pressure. So in this case, we don't want we want the system to be free to change its volume. We don't want the volume of the system to remain fixed, because usually when you make a glass, it is free to expand as much as it wants. The volume is not constraints. It's the pressure that is constraints. You are always at ambient atmospheric pressure. So the way to let the system adjust its volume in order to reach a zero pressure is to now do an NVT simulation, an isobaric MD simulation. So you will use a new fix. You will say, now I want to fix an NVT simulation, so NVT molecular dynamics simulation. So NVT, the number of atoms is fixed. Now the pressure is fixed, which means that the volume is free to change, but the pressure will be fixed, and T, the temperature, is fixed. So again, you will need to provide the temperature. So initial, final temperature. In this case, the temperature is 5,000. So we still want to mix the system at high temperature. We still need to put the damping factor for the thermostat, which should typically again be 100 times the time step, so 100 in this case. And then you need to provide the pressure that you want. What is the targeted pressure? So here this is done by putting the keyword ISO. This means that you want to provide an isostatic pressure, which is the same in the three direction. You want the pressure to be the same on X, Y, and Z. So you will use the keyword ISO, and then here you need to provide the initial and final pressure. Initial and final pressure. Again, in this case, those two numbers are the same, but if you want to gradually compress your system, for example, you can put initial pressure to be 0, final pressure to be something else, 1 gigapascal, 2 gigapascal, etc. In this case, since we are using real units, the units that LAMMPS is expecting is atmosphere. Again, you need a damping factor. This is to check how often will LAMMPS adjust the volume of the system. The way it works here is that you are fixing the pressure, not the volume, which means that if the pressure becomes higher than the pressure that you want, so if the system is experiencing some compression, then it means that the system should expand its volume. It means that the volume of the system is too small, it is compressed. So if you want the pressure to be zero, LAMMPS will increase the volume of the system so that the pressure can decrease and reach the targeted zero temperature that you want. On the other hand, if the pressure becomes negative, it means that in this case the system is under tension. So in the case of LAMMPS, the convention is that positive pressure means compression, negative pressure means tension. So in this case, if the pressure of the system becomes negative, it means that the system is experiencing some tension, which means that the volume is too large. The volume is too large for the system is experiencing some tension. So what LAMMPS will do is to decrease the volume of the system to release this tension and go back to a zero pressure. So again, you need to decide how often would you like to do that. So you need a new damping factor for the pressure, which tells you more or less how often will you adjust the volume in order to reach the targeted pressure. Again, in practice, this is a little bit more complicated than that. This describes more the inertia of the barostat that you are using, but we will talk more about this when we talk about thermostat and barostat. The next step here is that we want to cool the system. So after those two steps, so we have mixed the system at 5000 Kelvin. We now have also allowed the system to adjust the volume in order to reach a zero pressure. So at this point, you have achieved an equilibrium liquid, which is a liquid at 5000 Kelvin, which is at zero pressure. So the next step is at this point to start cooling the system. So now you will use a fixed NPT in which you still fix the temperature and the pressure, and this time you will decrease the temperature. So you will say that the temperature should be 5000 to begin with and be 300 at the end. And again, you need to put the damping factor, which is 100, and you need to say what is the pressure that you want. So again, we want the system to be able to adjust its volume so that when you cool the glass, it is free to change its volume in order to remain at zero pressure. So usually the higher the temperature, the higher will be the volume because of the thermal expansion. So since here we ask the system to remain at zero pressure, it means that the volume will gradually decrease because the system will be becoming more dense as you decrease the temperature. So we need, in this case, if we want to simulate a system at zero pressure, at atmospheric pressure, then we need to use the NPT ensemble. We need to fix the pressure to be zero and the volume will be adjusted accordingly. Again, we need to put the damping factor. In the case of the pressure, typically a good number for the damping factor is to be 1000 times the time step. So typically 1000 times the time step is a good number for this. In this case, the time step is 1 femtosecond. So a damping factor of 1000 femtoseconds or 1 picosecond, this is 1 picosecond in this case, is a good number. So those are, every time you use fix, you ask LAMMPS to provide, to perform a specific types of molecular dynamics, NVT, NPT, etc. So you need to provide some information about the temperature, you need to provide some information about the pressure, but the other thing that you need to provide is how long do you want the simulation to be? How many steps? So this is achieved by the command run. So run tells you how many steps of molecular dynamics, this is the number of steps. How many steps do you need to perform under those conditions? So for example, here in the first fix block, you impose the LAMMPS to do an NVT simulation at 5000 Kelvin, and you want LAMMPS to do this for 200,000 steps. Since each steps is 1 femtosecond, it means that here you are doing 200 picoseconds of molecular dynamics. You are doing 200,000 cycles of molecular dynamics. And LAMMPS will do that until you put the command unfix. So this means that here you start your fix, you start the simulation in the NVT assemble, and you call this fix 1. So this is the name of the fix. And LAMMPS will continue to do that for 200,000 steps. And as soon as you put the command unfix, you put here the name of the fix command that you put, and this will cancel the constraints. So here, when you open the fix, you define a new fix, which in this case, you define the new constraints that you want for your simulation. So you want a simulation to be in NVT, you want the temperature to be 5000, and those constraints are going to be applied until you unfix them. So here you put the name of those constraints. Those constraints are going to be applied until you unfix those constraints that you have called number 1. Same thing here, you open a new fix, you define some new constraints, which is now the dynamics needs to be in the NPT assemble. Now you want to fix the pressure, you want the pressure to be 0. These constraints will remain valid until you unfix this fix. So here we call this fix number 1 again. Those constraints are going to be active until we unfix, until we cancel those constraints that we added. And again, in this case, we want the NPT simulation to be performed for 100,000 femtoseconds, which is 100 picoseconds. Here, next step is to do the cooling. So again, we need to define how many steps are going to be used during the cooling. So this will define the cooling rate. The cooling rate is the change of temperature per unit of time. So in this case, we are the change of temperature is we go from 5000 to 300. So the change of temperature is 4700 Kelvin. This is the change of temperature. And here, the number of steps that we put here, we ask this NPT simulation to be performed for 4.7 million steps. It means that since each step is 1 femtosecond, it means that here we will have 4700 picoseconds of molecular dynamics. Okay, each 1000 steps corresponds to 1 picoseconds of dynamics. So here it means that your cooling rate will be 4700 divided by 4700. So it means that 1 Kelvin per picosecond. So here, depending on the number that you put here, depending on the number of steps that you want to be performed for this fixed, this will define the cooling rate. This will define how fast is your glass going to be cool, going to be quenched to 3000 Kelvin. Then the final step is to do the final relaxation here. So here we are going to do again an NPT simulation. In this case, the initial temperature is 300, final temperature is 300. Again, damping factor is 100 times the time step. We want the pressure to be isostatic again. Initial pressure is 0, final pressure is 0. Damping factor is 1000 times the time step. And we want to do that for 100,000 steps. So this is the final relaxation. This is the final chance that we give the system to further relax. So we want to do that in this case for another 100 picoseconds. And we close this fix. We open the fix and we close it, so we release those constraints. The final state, which you should always put, the final instruction that you should always put at the end of the simulation, is to write the final configuration. This is very important to always do that. So the configuration is the position of the atoms. You always want to make sure at the end of a simulation, you always save the final position of the atoms. This is important because if you want to continue further this simulation or do a new simulation that now is applied on the silica glass that you just generated, you don't want to keep redoing the same simulation over and over. What you want to do is to perform one simulation to, in this case, make a silica glass, then save the final position of the atoms, the configuration of the silica glass, and then possibly for a next simulation reuse as a starting point this new configuration that you just generated. You don't want to keep redoing the same simulation over and over. So it's important to always finish simulation by writing the final configuration, and this can be used by using the command write data. So the command write data, what it will do is to save the final position of the atoms and save it in a new data file. So this data file will have exactly the same format as the initial data file that we provided to LAMMPS. This is the file that contains the geometry of the system and the position of the atoms, the types of each atom, etc. So this new file will now be generated by LAMMPS. It will contain the final position of the atoms after all those instructions. And in the future, if you want to run a new simulation, you can use this new data file as a new starting point. If you want to run a simulation about the silica glass, you can use this final configuration directly. It has exactly the same format as a data file that you would use as a starting point for a new simulation. Usually, we also want to write a restart file. A restart file is almost the same as a data file, but it contains more information about the system. It contains some information potentially about the potential, about the types of other parameters that you have defined in your simulation. So it makes it easier to easily restart a file, restart a simulation. So usually, again, we will use the command write restart. In both cases, for write data or write restart, you need to use the command and then provide the name of the files where you want to save this information. In this case, it means that LAMMPS will create a new file which is s300k.dat that will contain the information about the data file, and will also create a new file s300k.rest, which will be the restart file that can be used later on. So it's always important to finish the simulation to avoid to put this information at the end of the simulation so that you can directly reuse the outcome of this simulation for any subsequent simulation. In this case, we decided to put the information about the potential in a separated file. So those information can be put in the same main input file, but it's usually a good idea to put it in a different file to simplify a little bit the main input file, make it a little bit lighter. So in this case, in this file, we will put all the information about the types of potential, the types of interatomic energy that we are using, which is a very important parameters for the molecular dynamics simulation. And what are the parameters? What is the parameters for the potential? So here in this case, we will be using the BKS potential. So this is a potential that works quite well for glassy silicon. And in this case, this potential relies on a Buckingham form. So the potential for a Buckingham potential has the following form. First, you have the Coulombic interaction, so 1 over 4 pi epsilon 0 times the distance times the product of the charges. Then you have a second term, which is the electronic repulsion, which is A times an exponential decay function. And you have the last term, which is the van der Waals terms, which decrease as 1 over R6. So this potential is defined for each pair of atoms. So for each pair of atom I, J, where I can be, for example, 1 if it's for silicon, 2 is for an oxygen atom, you need to define what is the interatomic energy. So the product of the charge here depends on the types of each pair of atom I and J. The parameter A is also going to be different for each pair of atom. The parameter rho here in the exponential decay function also needs to be specified for each pair of atom ij. And the last parameter is the parameter C that also needs to be defined for each pair of atoms. So what you need to tell LAMMPS first is what types of potential do you want to use for each pair of atoms. So here we are going to use a Buckingham form, but there is many different forms of potential that can be used. And you need to tell what is the value of those parameters for each type of elements. So the way to define the type of atom is to use the pair style command, which tells you the type of potential that you are using. So here we are using the buck/cool/long parameter, which tells us that we want to combine a Buckingham potential, so which is this part of the potential, plus the Coulombic interaction. So this is the Coulombic part, this is the Buckingham part. So each parameter comes with a different, each type of potential comes with a different keyword. So here we are saying that we want to combine a Buckingham potential with some Coulombic interaction. Here we specify two parameters, which are the cutoff. The first one is the cutoff, the distance cutoff for the Buckingham interaction. The second number is the cutoff for the Coulombic interaction. What does this cutoff means? It means that if two atoms are further away than, for example, 5.5 angstrom, which is the first cutoff, then we consider that the Buckingham energy term is just going to be 0. This is to save some time. We know that if we plot the energy as a function of the distance, at large distance the energy goes to 0. So rather than calculating a lot of energy terms between each pair of atoms, we are going to say that if the distance is larger than a given cutoff, we will just say that the energy is 0. The energy would be very small, so we just say that it doesn't contribute so much to the total energy of the system. So we will just say that the energy after the cutoff between two atoms, a pair of atoms, will be just 0 if they are far away from each other. So here, since the Coulombic interaction decreases rather slowly with the distance, it decreases 1/r, we have to use a large cutoff. So here we use 10 angstrom, but for the Buckingham potential, it decreases very fast with the distance. It decreases 1/r6. So we can use a smaller cutoff of 5.5 angstrom in this case. So for each types of potential, usually you would find what is the right cutoff to choose. Then the second thing is, after we have specified the type of potential, so here Buckingham and Coulombic potential, after we have specified the cutoff, we need to specify what are the potential parameters. So LAMMPS already knows the charges, so we have defined the charge of each atom in the data file. We have said that for silicon, the charge is going to be 2.4, and for oxygen, the charge is going to be minus 1.2. So LAMMPS will already be able to calculate the Coulombic interaction. But we need to specify now the parameter A, the parameter ρ, and the parameter C. And we need to specify this for each pair of atoms. So this is accomplished by the command pair coef, which is used to define the potential coefficients. So here, each line first should start with two numbers. Those are the two types of atoms. So you need to specify the potential parameter for each pair of atoms. So for example, the first line will give you the parameters for when silicon interact with another silicon. The second one will tell you when silicon interact with oxygen, and the third line will be when oxygen interact with oxygen. That is to say, the potential interaction between the atoms of type 2 and other atoms of type 2, oxygen, oxygen. And then the three following parameters will be the parameter A. So the first term will be the pre-exponential term A. The second parameter is ρ, so the term inside the exponential decay function. And the last parameters is going to be C. So in this case, again, those numbers are following the convention that you are using for the units. So those numbers will depend on the types of units that you are using. For example, in this case, since we are using real units, A will have the units of an energy. So it's going to be, in this case, in kilocalorie per mole. and rho, for example, will be in angstrom, okay, which is the units for the distance. Using those lines, LAMMPS will know the types of potential that you are using, the cutoff, and the parameters for each types of atom. The next step is there is a few more parameters to specify. So first, you have this line here that tells us how to calculate the long-range Coulombic interaction. So we will come back to this in a subsequent video. So we need to specify a few, what is the method that we are using for this, which in this case is the eval function. We need to specify here a conversion criterion. So I'm not going to go into details of this, but this is for the Coulombic interaction, and in this case it depends for each system. This line should not be changed. You have a line about the neighbor lists. Again, we will come back to this in a subsequent video, but this line should stay as it is. Again, the neighbor modify will not cover this time. The last line that is interesting is the time step. So this common time step defines what is the integration time step. This is the time step that you are using when you integrate the acceleration to calculate the change, the variation in the velocity, and then the variation in the position. So this time step is very important. It needs to be small enough so that the numerical integration is correct, so that you can take only the first order expansion, the Taylor expansion of the velocity and of the position. Again, so this time step is a time, so it comes with a unit. In this case, we are using real unit, so this time step is expressed in 1 femtosecond. In this case, it means that the time step is 1 femtosecond. So this time step tells you the duration of the simulation. For example, if you are requesting a molecular dynamics for 100,000 steps, it means that you will do a molecular dynamics of 100,000 femtosecond, which is 100 picosecond. So the time steps gives you the duration between each molecular dynamics steps. So those are all the input files that you need to provide. Again, the data file that contains the position, the geometry of the system, the main input file that contains all the instruction, potentially a file for the potential details. With those information, LAMMPS will start having all the variables, all the parameters, all the instruction that you want to perform. LAMMPS will start the calculation and in return gives you some output file which give you the outcome of the simulation. So here is the list of the typical output file that LAMMPS will provide you. So the first thing is that, assuming that you request it, but you should always request it, LAMMPS will give you a final data file. So this data file is the file that is created when you use the command write data at the end of the input file. And this data file contains the final configuration, so the final position, but also the final velocities of the atoms at the end of the simulation. It has exactly the same format as the initial data file that you started your simulation with, so it means that it can be directly used to start a new simulation. It will have the same exact format. You can directly reuse it as the new starting point for a new simulation. The second file is the trajectory file. So this is the file that is created by the command dump. It contains all the information that are atom specific. So these types will contain, for example, the position of the atoms every n steps, or it can also contain the velocity of all the atoms, etc. So this is the file that you can use to see how the atoms are moving according to time. So this is the file that you can use for the visualization software that are going to show you the motion of the atoms. This is also a file that can be used whenever you need to calculate some further properties that are atom specific, that depends on the position of the atoms. This is the file that will contain all the necessary information for this. Then you always have a file that is a log file that is created, log.lamps. This file typically contains everything. LAMMPS will store in this file all the information about what it is doing and a lot of information about the simulation itself. Typically, this is a file that is useful to look when something goes wrong. If the simulation is stopping, if there is an error message, this is in this file that you will first find what is the error message and try to understand what went wrong. Why did the simulation stop? Why you did not get what you were expected? This is in this file that you will find all useful information that can be used to try to debug the input file. The last file is the output file. So the main output file is going to be a file that contains a summary of all the actions that are executed by LAMMPS. For example, if you request LAMMPS to perform an energy minimization and then a molecular dynamics in the NVT assemble, then molecular dynamics in the NPT assemble, then LAMMPS will tell you a summary of everything that it does. And it will also provide all the thermodynamical data. So everything that you put in the thermostyle command, so all the thermodynamical data that are defined for the whole system, the temperature, the pressure, the potential energy, the size of the system, its volume, its density, all those information that are defined for the whole system will be provided in the output file. Let's go through the format of all those output files one by one. So the first one is the trajectory file. So it has the following format. First, you will see the following keywords, and here the first thing you will see is the time step number. So in this case, this is for time step 0, so which is the first step of the simulation before it begins, which is always going to be written as a starting point by LAMMPS. The second information that you find here is the number of atoms. Those are information that can be used by a software that can display the motion of the atoms. So they need those information about the numbers and the time step number. Then you have the size of the box here. So those are the X low and high, X high parameters that gives you the extent of the box on the free axis. And then you have the list of all the atoms with, again, the following format. You have first the atom ID. Be careful that sometimes the atoms got mixed up, so it's not necessarily ordered 1, 2, 3, 4, 5. Okay, they can be ranked in different orders. Then you have the type with the same format as the one we had before, 1 being silicon, 2 being oxygen, and then you have the position X, Y, and Z for each atom. And this will be repeated for all the atoms. So here you will have 3000 lines for all the atoms. And then for each new time step, you will get this entire box. You will get this entire block for each time step. So this will be repeated for every time step that is stored inside the trajectory file. The next file that is very useful is the main output file, which contains everything about what LAMMPS is doing and the thermodynamical data of the system. So this file will typically look like this. So first, we will have some information about which LAMMPS version is being used, so the version number. Then LAMMPS will tell you every time it does an action. For example, it will tell you, I am reading the data file. Here are the information that I find that the box is going from 0 to 35.1. Here is the number of processors that are used for this simulation. I am reading the position of the atoms. I found 3000 atoms. Now I'm reading the velocities. I found 3000 velocities. You have a couple of information about the internal stuff that LAMMPS is doing. And then, more importantly, LAMMPS will tell you the thermodynamical properties of the system. For example, here, this is where you are starting the first energy minimization. So every time you provide a new instruction to LAMMPS, like doing an energy minimization, doing an NVT simulation or an NPT simulation, LAMMPS will tell you, okay, I'm starting this minimization. Here is the unit system that I use. And then you will have all the thermodynamical properties of your system as the simulation goes. So here, those are the information during the energy minimization. You have for different step numbers, so every 100 steps, LAMMPS provides you first the temperature. So the second column here is the temperature. provides you the potential energy. So this shows you the potential energy. The potential energy decreases with the number of steps. This is because we are doing the energy minimization. So the energy of the system decreases as we perform this energy minimization. Here you have the pressure of the system. Here we have a very high initial pressure because the volume is not adjusted yet. So this is the pressure in atmosphere. Then you have the volume here, which is the next element, volume in cubic angstrom. You have the size Lx of the box. In this case, the size of the box on the x-axis is not changing, so it's 35.1. This is the same box length as we used in the data file. And the last information is the density in gram per cubic centimeter. So those are all the thermodynamical properties that you requested using the thermostyle command in the input file, and LAMMPS will provide you those properties as a function of the number of steps during all the energy minimization, NVT, NPT, molecular dynamics simulation, etc. So those are some information that you can use to check what is the state of the system, what is its pressure according to time, its velocity, its temperature according to time, its volume, etc. The last piece of information that is always useful is at the end of each instruction, for example, at the end of the first energy minimization, when the energy has been minimized, LAMMPS will tell you how long it took to perform this action. So here this number, 200 seconds, so here this time is in seconds, tells you how long it took for LAMMPS to perform this energy minimization. It tells you that it took 200 seconds with one processor to perform those 257 steps of energy minimization for the 3000 atoms. So this is an information that is always useful to be able to predict for a given simulation how long is it going to take before it finishes, so that you can plan accordingly how many processors are you choosing for this simulation, how much time do you allocate for this simulation to finish. The last thing is how to run LAMMPS. So you will have different options, whether you run LAMMPS on your laptop or whether you want to run LAMMPS on the university cluster. So let's go through the different options that you have. So the first option for small simulation, small system, or small duration is to just run it on your laptop. So you can certainly download LAMMPS and install it on Windows, Mac OS, etc. And then you can run simulation on your own desktop or laptop. So for this, LAMMPS doesn't come with any graphical interface, so you will necessarily need to use a command line terminal. So if you are using Mac OS, you will have to use the terminal, which is pre-installed on all Mac. And if you are using Windows, you will need to use the command prompt. Then you will need to go to the directory where you want to run the simulation. So we will see more details about how to use the terminal in another simulation, but you will need to go to this specific directory. Again, each new simulation should be performed in a new directory. And the way to run LAMMPS, once you have placed all the input file in this directory, will be to use the following command. If you are running LAMMPS on macOS, you will need to use the command LAMMPS. So type the command LAMMPS, then using the symbol smaller than, then put the name of your input file. So this would be the name of the input file. Then use the symbol larger than, and here you want to put the name of the output file that you want LAMMPS to create. Okay, so the command is roughly similar for Windows, except that you will have to replace the smaller than and larger than symbols by -in and -out, but the idea is the same. You just indicate the name of the input file that is already present. So this is what the instruction that LAMMPS is going to use, and here this is the name of the output file that is to be created by LAMMPS to give you the outcome of the simulation. However, most likely you will be using the Hoffman cluster to run your simulation on the UCLA cluster. So here is how it works. Again, we will most likely have a separate video to see how to connect to Hoffman and how to transfer your input file there and how to start running simulation. But basically the idea is roughly similar as if you were to run those simulation on your laptop. Again, you will need to use the terminal to be able to connect to Hoffman and send some instruction. You will need to go to the directory where you want to run the specific simulation. Make sure all the input files that you need are placed in this directory. Then you will need to create a submission file. So the reason is that the cluster, UCLA cluster, is shared by everybody at UCLA. So you cannot just submit and run your simulation just like this. You need to submit your simulation, then all the simulation will go into a queuing system, and then as soon as there is a processor available, then your simulation will be allocated to this processor or this group of processors and will start running as soon as possible. So the way to submit your simulation is as follows. So you use the command lamps.q. This will create some kind of small script that is going to ask you a few questions about the simulation that you want to run. So you have a few options. You will need to type B, capital B. This is to build a new submission file. Then this script will ask you what is the name of the input file that you want to use for this simulation. So here you will type the in.something, whatever is the name of the input file that you want to run for this simulation. You will need to choose how much memory you want to allocate to this job. So here typically we always use 248, but this might depend on each job. If you have a very large system that requires more memory, you might need to increase the memory that you request, but typically 2000 megabytes is the right number. Then you will need to choose how much time you want your simulation to run. So you always have to specify how much time are you asking, how much computing time are you asking. It doesn't mean that it's the time that your simulation is going to take. It means that it's the time that you request on the cluster. So you always have to make sure that you request enough time for your simulation, because if you don't request enough time, then your simulation won't have enough time to finish and it will stop before it can finish because you reach the maximum amount of time. So usually it's always good to ask as little time as possible, because the lower the amount of time that you ask, the higher will be your priority. For example, if you know you are going to run a very small simulation, you can ask for only 1 hour, then you will have a very high priority because you will only use the processor for 1 hour and then release the processor and it can be used for anybody else. If you ask for more time, for example 24 hours, then your priority will be a little bit lower because you are asking for more, so you might have to wait in the queuing line a little bit longer. So typically you can use, for example, 8 hours is typically the time that it takes to quench a glass of around 3000 atoms. So you will be able to achieve something like around 5 nanoseconds of molecular dynamics with if you use 16 cores. But if your simulation is longer, you can ask for more. You can ask for 24 hours. Typically, we always want to keep the simulation less than 24 hours. If you want to request more than 24 hours, you need to wonder first, is it really needed? Can I just not cut my simulation into smaller tasks? And if you absolutely need more than 24 hours, then we will need to use our private cores, but you probably want to talk to me about this. This next option, the script will actually ask you whether you want to use our resource grab cores or if you just want to use the shared core. So we typically have some cores that are just dedicated to our group, but we really keep really try to keep those cores, those processors, only for either the important project that we have, or only for the simulation that really requires more than 24 hours. So here, whenever possible, try to say no. It doesn't change anything. It does just mean that you will not use our private processors, but use the shared processors. So as long as your simulation is lower than 24 hours, then it's perfectly fine to use the public, the shared processors. The only reason you might want to use the private processors is if your simulation is longer than 24 hours. The next step is how many cores would you like? So typically 16 or 8 cores is a good number. If you start to ask for more than that, of course, the more cores you ask, so the more processors, the faster your simulation will be. But if you ask for too much, you will lose some efficiency. The processors will have to keep waiting each other, communicating with each other. So typically 16 or 8 is a good number. After that, the script will ask you whether you want to submit your simulation now. So if so, you will tap Y for yes, and then you will just type Q to quit, and your simulation will start running. At least it will be added to the queuing list, and you will be able to see what is the priority of your job, and you can see when it is likely to start. To see the list of all your simulations that are either presently running or that are waiting to run, you can use the command myjobs. Myjobs, the command myjobs that you would type in the terminal here, will tell you the list of all the jobs that you have presently running or waiting. So the way to know if your job is presently running or not is to look at the state of your job. If it's R, then it's a job that is presently running. As soon as the job finishes, either because the simulation has finished, either because you have reached the time limit, it will just disappear from this list. If you have a job that is QW, then it means that it's in the queuing line. So it's still waiting. It's waiting for processors to free up in order to start. You can have some information about when did you submit the job? When did the job start? You have some information about where the job is actually running, in which nodes. Here is the number of cores that you are requesting, so 8 cores, 16 cores, etc. Here is the name of your job. This is you, and this is the priority. So this is the priority of your job. So the higher the priority, the less time you will wait in the queue. So it's always good to try to ask for either a low number of processors or a low amount of time. This is a good way to increase your priority so that you will wait a lower amount of time in the queue, because your priority will be higher. And this here is the ID of each simulation. So every time you run a new simulation, every time you run a new job, it gets a new ID. Which is good in case you, for example, need to delete this job. If you start a simulation, realize that there is something wrong, you want to delete this specific job, what you can do is type the command qdel and then add the ID, the specific ID of the job that you want to delete, and this will stop the simulation. Otherwise, the simulation will just go on. Even if you close the terminal, if you turn off your laptop, the simulation will just go on the Hoffman cluster unless you delete it with the command qdel. Okay, so this is it for this short introduction to LAMMPS. We will see more videos to see a few more detailed functions of LAMMPS and how to use it in practice. I hope this was useful, and thank you for watching.